So once again, we want to say good evening to everybody, and I'm Joe Deli Carpini, the Science and Operations Officer. With me tonight, we have Hayden Frank, one of our lead meteorologists, and two of our meteorologists, Andrew Lacanto and Rodney Chai, who will be all presenting this event review for you tonight. So with that, I'm going to hand it off, I believe, to Hayden, who will get us started with the review of this storm.
All right, great. Thank you, Joe. So this is just a look at the basic track of the low pressure system that brought the snow to the region. And as we observed, it was a big snowstorm in southern New England. A lot of places averaged around a foot of snow. But what you'll notice is there were some extremely high snowfall amounts across portions of New York State, into parts of central and southern New Hampshire and Vermont. We had places come in with over 40 inches of snow, believe it or not. Binghamton, New York, for example, had 40 inches of snow. That's where Joe started off his career. So some really impressive stuff. One thing that you'll notice here, this was the surface low that passed near Nantucket. These numbers where it says 995, 1,000, that's actually the pressure of the storm. And believe it or not, this was a relatively, at the surface, a relatively weak low pressure system compared to some of the other coastal storms we have. But it's not all dictated at the surface, and we're going to talk more about that, and Andrew Rodney will really get into that, but it's what's going on at all levels of the atmosphere. So you kind of have to think of it in multi-dimensional instead of just a flat surface there. So these were some pictures from around the region during the event. You can see the upper left there is in Boston, Worcester. There's one down Mashpee, and another one in central Massachusetts. So this was a fairly widespread. It wasn't confined to the interior. A lot of places average between 8 and 14 inches of snow. So it wasn't a blockbuster for us, but it was definitely a major winter storm. And as we go along, this actually was shot by Rodney, and it was the comment, really puking snow in Attleboro. So that's kind of a meteorologist expression of a very heavy snow, and you can see the visibility in that imagery there. Usually the delineation for heavy snow is once you start to get visibility a quarter mile or less, to give you a rough estimate there. And some more pictures. The one on the left actually is from my house in Westboro. And if you look to the middle one, that's Frank Nocera, another one of our forecasters from his house in Rhode Island. And Joe's on the right. So you can see fairly consistent snowfall across the region from these pictures. And then again, someone on skis, a good way to get around that day in Boston. And you can see not much going on in the city that day other than a lot of shoveling. So it was something that was well forecast. We were pretty prepared for this, a couple days out. And I believe these photos were taken the evening after the snow event. This is from Bryce Williams. He's another forecaster at office, and he also does a lot of photography on the side. So these are some really nice pictures the evening after the storm. So kind of go into the basics here of how we kind of go into a forecast. And this table may give you a headache there. It's a bunch of numbers. But in reality, what it is, it's different fields we look at, such as temperature, wind speeds, pressure, and it compares it to climatology. And where you see the numbers are really negative or really high, that's giving you an indication that it's very unusual to see those parameters high. Well, if you have an unusual, say, wind speed or temperature or whatever thing you're looking at, that can give you an idea that, hey, this could be the potential of a significant storm if some other things come together. So it's kind of like a red flag for forecasters to look at it, give someone a heads up, hey, this is not normal. This is how extreme this type of event could be. So, for those of you who follow, meteorology more, more than some other, casual observers, one thing you'll notice is you'll hear us talk about weather models. And then there's what are called ensemble models. And that's just tweaking the initial condition of that same model, which can in turn make a very big difference in the outcome because they're very sensitive. A little tweak here and there where the pressure is, 3 days later can make a significant impact. So this was for Boston. And the GFS model had been the most south. It was reluctant to bring the heavy snow further north. So basically, the mean there is what the average of the models had around 4 inches in Boston. But this is why ensembles can be helpful. This is looking at about 72 hours before the event. Look at the potential spread. We have up to 15 inches to barely anything. So that's giving an indication that there's a lot of spread in the model and a lot of opportunity for it to go higher or lower. That tells us not only is there uncertainty, but we're going to have to look at other models. What were the other models, such as, say, the European model and that type of information as we go along here. And Rodney will touch on that in a little bit here. So we kind of talked about this at the beginning. Just looking at where the surface low pressure system is can give you an idea, but it's not the end-all answer. Remember, we're looking at the atmosphere, not just at the surface, but what's it doing, say, 10,000 feet above our heads? Well, this was a profile of that at that level. And what you'll see in red there, you basically have winds of 80 miles per hour in that area. Now, that's over eastern Massachusetts. If you go just north of there, there's barely any wind, and it's light out of the east. Well, think about this. Wind is coming together at very strong speeds. What's going to happen? Well, it has nowhere else to go, right? It's going to be forced up. Well, you get that convergence, that air mass is forced up, and you get heavy rain, or in this case, if it's cold enough, heavy snow. And that's what we tend to look at as meteorologists to give us support, give us confidence in the type of forecast and what we might see. And another way to look at that is something called frontogenesis. It's basically a front in a different level of the atmosphere, not necessarily at the surface. We were all cold that day, right? Everyone was, pretty much but well below freezing, except probably like the Cape and Islands. But for the most part, everyone was, well below freezing. But what was it at 10,000 feet? Okay, you see where that shading is of red and blue? There's a front at that level, okay? So you have convergence right at 10,000 feet, those strong winds coming together, forcing that air up. And that could be one area of heavy snow. Now, you can also have another front, say, at 5,000 feet. That could bring heavy snow in another band further south. So there's a lot of moving parts to this. And as we spoke, this is at 850 millibars. Now, you don't see the 850 at that level. The front is way south. So we were all in the cold air. But what you'll notice is there's strong flow off the ocean. We're looking at almost 30 to 50 knots of wind off the ocean. Well, we always know the ocean has a ton of moisture. So that's only going to help to bring us rain, or in this case, snow, because it was cold enough. So again, a lot of different elements, a lot of different things to look at as a forecaster. And with that being said, I am going to turn it over to Roddy now, who's going to talk about something called high resolution models. These are really useful as you get inside, say, 36 or 48 hours of the forecast to kind of give you specific details of what might happen. So with that, I will turn it over to Roddy.
Thank you so much, Hayden. And as Hayden mentioned, these are high resolution models, and in this case, this is the high resolution ensemble forecast model, or the HREF, and we really like to use this ensemble model, especially when we get to 24 to 36 hours. Now it has a lot of skew in not only predicting the type, intensity of precipitation, but also kind of give you the ballpark where to expect the heaviest precipitation. And in this case, this is an ensemble model, which is basically combining different individual models, and we like to look at ensemble guidance because, if, the different models may have their own uniqueness and different outcomes, but if, they kind of converge on a similar solution, it gives us more confidence when we forecast the weather. And in this case, what you're looking at is the most likely precipitation type and intensity. And this is looking at 1 a.m. On December 17. And you can see the darker shadings represent heavier precipitation, and you can see a pretty wide swath of moderate to heavy snowfall across much of southern New England. And this is a classic signature of, when you have warm air overrunning the colder air underneath, and this is a kind of setup. If the temperature is cold enough, it will give you widespread moderate to heavy snowfall. And this is pretty much snowing everywhere in southern New England at 1 a.m. And this is looking at the hourly snowfall. And once again, this is on the ensemble mean. And even taking the mean, you have areas that are exceeding 2 inches per hour snowfall rate. And don't get fixated about the exact location where the bullseye is. It really want to show you the potential for 2 inches plus per hour snowfall rate somewhere across southern New England. And this has implications on for our partners, in public safety, like Department of Transportation, emergency management, and this, the HREF showing heavy snowfall rate gives us more confidence in the messaging that this would be kind of a higher impact snowstorm. All right, and look, fast forwarding 6 hours, 7 a.m., December 17, and you can see that now, the HREF is depicting kind of 2 areas of heavy snow band, one kind of across central New York into New Hampshire, and the other one across Boston into Providence. And that is actually co-located with the coastal front. And, if you are west of the coastal front, you're snowing. You are east of the coastal front, you may be mixed with rain or actually just plain rain. And some of you who live along the South Coast and the Cape and Islands may remember a flip to rain or rain-snow mix kind of around morning rush hour. And that's because the coastal front is hung up kind of right around Plymouth County down to the Cape Cod Canal. So there was a few hours whereby when the snow actually changed over to rain before it changed back to snow as the cold front moved through and resulted in a flash freeze, which we'll talk about a little bit more later. And this is the, once again, the hourly snowfall rate, and this is the mean, and it's trying to show, heavier snowfall rate 1 inch per hour from the Boston to Providence corridor. And also a bit further north, you can see over 2 inches per hour snowfall rate in southern Vermont and New Hampshire. And this is looking at the 24-hour total snowfall. And I want to point out to you, this is called the probability match mean. And what that means is that it is a more complicated way of computing the mean. So instead of like taking, let's say, you have, a model may show 1 inch, another model might show 15 inches. The simple mean in this case would be 8 inches. But a probability match mean kind of capture the extreme solutions of different models. And so when computing the mean, it preserves the higher amplitude solution. So you can see, across central New York, there's close to 30 inches of snow, and kind of towards northeastern Pennsylvania, towards southern New Hampshire and Vermont. And actually, this is a very good approximation of what actually panned out. as you remember, Hayden talked about some of these areas have received over 40 inches of snow, including places like Binghamton and, up towards Lake Winnipesaukee in New Hampshire. So that's actually a very good depiction of what actually happened. And taking a look at the ensemble members, if you lay them out side by side, just a little background on HREF. It's actually, it comprises of 10 different members, and actually specifically it's 5 different models, but 2 time steps. So some of you may have heard of the windshield wiper effect. Basically for the snow, people who love snow out there, the windshield wiper effect is basically, 6 p.m. the model shows 24 inches of snow, and then 12 hours later it shows very little snow, and then the model flip-flopping. And so the HREF tries to minimize windshield wiping by incorporating 2 different time steps. So if the model is flip-flop, then the HREF can minimize the flip-flopping. So in this case, it shows the different members show remarkable consistency in not only the intensity of the snowfall, but also the placement. And this is called the NBM, the National Blend of Models. And this is actually a key part of the National Weather Service mission to help help us become a weather-ready nation. And the NBM basically helps to make the forecast from different offices across the country more consistent. And the NBM, as the name suggests, it is a blend of different models. And you would have it basically blend models like the European, Canadian, the GFS, and different high-res models. And it has very good skill because it will blend the models in such a way that it would try to improve the accuracy of the forecasting. And so basically this has a lot of skill, and what you're looking at is this is the 10 percentile snowfall, and this is kind of at least expect this much snow. And then this is the 50th percentile, kind of like, if you like it, this is like the median. And so this is kind of like the best guess of how much snow you can reasonably expect to receive. And basically it's showing a wide swath of, 10 to 12 inches of snow, which is actually pretty close to what most of our area receive. And this is the 90th percentile snowfall, so this is the potential for this much snow. This is kind of like the worst case scenario. And the worst case scenario actually pan out in the areas that receive up to 40 inches of snow, again from central New York to southern Vermont and New Hampshire. And taking a look at the comparison between the NBM point forecast and what was actually observed. So if we take the 50th percentile, you can see very close, for our 4 climate sites, like Boston, 12.7 inches, the NBM predicted close to a foot of snow. And likewise in Providence, it's basically 8 inches versus 7 inches. So the NBM 50th percentile verified very well. But also note the difference between the 10th percentile and the 90th percentile. So, there's model uncertainty. And, one of our challenges as forecasters is to communicate the uncertainty to the public, because we understand that, you would like to, know exactly how much snow you're going to get, but sometimes it's very difficult because due to the different factors and dynamics, as like Hayden mentioned, the surface low pressure wasn't at all that impressive. In fact, the surface low was weakening as it crossed south of southern New England, but the dynamics in the upper levels compensated for the weak surface low pressure. So in this case, the upper level dynamics won out. But in other situations, if the dynamics are not that strong, if the temperature is not as cold, then probably we would have received closer to the 10th percentile. So in this, so a lot of moving parts, but we were fortunate that the 50th percentile panned out. And this is taking a look at, this is actually one of our briefing packages to our partners. Think about emergency management and Department of Transportation. And so we broke down into the hazards into different types. And clearly in this case, the biggest hazards were the heavy snow, and to some extent the strong winds, and minor coastal flooding. And I want to mention flash freeze. That's really more for the South Coast and the Cape and Islands, because remember, the temperatures actually warmed up into the mid-30s for these areas, and it changed over to rain. But then there was a sharp cold front, that coincided with the tail end of the rush hour. So there was actually concern that the highways may become a sheet of ice, and basically across southeast Massachusetts and southern Rhode Island. So the flash freeze was actually a key concern for these areas. And so this was the official snowfall map that we sent out. I believe it's the last one before the snowstorm, and you can see a sharp cutoff towards southern Rhode Island and towards the Cape and Islands, and Nantucket and Block Island barely got any snow. But then just if you move just inland from the Cape Cod Canal, you're talking about a foot of snow. And this is the max wind gust forecast. Really, the maximum wind gusts were focused more towards the Cape and Islands and the South Coast, and further inland, it's more run-of-the-mill wind gusts in a nor'easter. And this is something called the Winter Storm Severity Index, the WSSI. In fact, our meteorologist in charge, Andy Nash, he's actually the branch, the creator of this WSSI. And this basically, it's we always try to improve our messaging, and WSSI is actually one of the ways we try to do that with the public. So by using, by looking at the map, looking at the color scale, your focus is immediately drawn to the orange and red colors, which represent the more severe areas that will receive the more severe impacts of the storm. And basically, it's a wide swath of moderate impacts and actually quite a good amount of major impacts. You can even see extreme impacts towards just southwest of our area. And you may wonder why the southern areas have major impacts, and that's because of the snow loading and flash freeze. And in this case, the heavy snowfall is also a concern, but the flash freeze and snow loading, especially in areas where the temperatures are more marginal, the snow is heavier and wetter, and when you get this amount, like a foot of heavy wet snow, you're going to get power outages. And flash freeze, like I mentioned, makes for very hazardous travel. And the next 3 slides is just to show you, as the heavy snow moved in. This is the Charles River in Boston, and you can see the visibility really became terrible as the heavy snow moved in. I can barely see anything now. And so this is actually a very cool visible satellite imagery loop of this is actually towards the tail end of the nor'easter as it was pulling away. That era of kind of low pressure towards the end, or towards the south of southern New England. That's actually, gravity waves as a result of the intensity of the storm. And you can see, if you look at, there's some ripples actually kind of straddling between Long Island in New York and Connecticut. And those ripples are actually gravity waves that, just as a result of the sheer intensity of the storm. And those were actually producing moderate to heavy snowfall as the nor'easter pulled away. So very cool stuff. And you can also see, the white swath of snow cover left behind, towards the left side of the satellite image. So very cool stuff. So this is taking a look at our official forecast on the left-hand side and the observed snowfall on the right-hand side. And we just want to thank everyone who submitted snowfall reports, and that those are very, very helpful, and it helps us to verify the forecast. And in this case, you can see the observed snowfall matched the forecast quite well. So thanks to everyone. And this is a graphic showing the record-breaking daily snowfall, for our 4 climate sites. Basically, all the 4 climate sites broke the daily snowfall record. So it was a pretty major winter storm. So at this point, I would pass the presentation to Andrew, who's going to take you to the end of the presentation.
All right, thank you, Rodney. So as you all can see on your screen, this is essentially it's the temperature loop of basically a good part of New England, which basically spans through the overnight hours of Thursday morning, and then lasting into the sort of early to mid afternoon hours on Thursday. And what we find is what you'll see in the text box there is earlier on in the loop, you'll see this thing called the coastal front, which basically it's a sharp gradient in temperature that we see near the coast. And as you can sort of see there, just look at that sharp gradient there that's setting up between Boston is 35 degrees, but look at Worcester, it's 17, Springfield's 20, Hartford's 21. And eventually what happens is as the day moves on, especially into the mid to late morning into the early afternoon, is that as the coastal front starts to, what happens is it collapses and shifts southeastward into those areas where it's been above freezing. So your ground is, instead of it being snow covered, across portions of Bristol and Plymouth counties in Massachusetts, Cape Cod, a good part of Rhode Island, much of the area there is above freezing. And what we see is that as the coastal front collapses, all that colder air, that basically that teens to 20 degree air, that all comes crashing down on southeast Massachusetts and the south coast into Rhode Island and eastern Connecticut. And what will happen in that situation is that any sort of water that's on the road will freeze very quickly, and that's what we call a flash freeze. And that's very dangerous, especially if it coincides with either the morning or the evening commutes. And in this case here, fortunately, the greatest impact was really sort of after the commute, but you still had falling temperatures through the 20s, lasting a good part of the day, the rest of the afternoon. So moving on here, this is Hayden had showed the 700 millibar, or about 10,000 feet above your head. This is a similar image, but this is sort of a more focused on the very, very near term, say within the next 3 to 6 hours. And what we'll see here is this is a map of what we call temperature advection, which essentially what that does is that shows where warmer air is rushing in, or where colder air is rushing in, colored blue. But the area that we sort of want you to focus on is that area in the red. And that's what we call warm advection. In other words, temperatures are basically warming aloft as this as that band of that sort of east-west band of warm temperature advection spreads across central, really a good part of interior Massachusetts, Connecticut, and into even towards the eastern and northeast Massachusetts, and that tends to support a band of heavy snow. And as we move on here, we'll take a look here at what's called frontogenesis, and that's another meteorological term. What that means is that there's a strengthening front at that level. And what you see, look very carefully, is that if you look at the last image and compare it to this one, you'll see very strong frontogenesis, basically right where that axis of warm advection was. And that's something that we see commonly with these sort of scenarios, and that tends to support bands of heavy snow. And you can see that that contrast there. And this is the morning the meso-analysis of surface sea level pressure and the radar imagery at that time. And you can see the low pressure there is just east of eastern New Jersey, near the Jersey coast. And it's sort of just ramping up at this point in time. But the one thing, if you look at the radar imagery, those are those blues, the greens that are colored on the image. The heavy snow really lines up quite well with the 700 millibar warm advection and frontogenesis that we were sort of just pointing out. And as we'll sort of see that as sort of a theme with these winter storms, is that oftentimes at that layer, when you see that warm advection and you see that frontogenesis that it's very strong, you'll tend to get these sort of bands of, locally heavy snows like we saw, which really extended. We certainly got quite a bit of snow here, but areas just to our north and west, central New York, southern Vermont, into central New Hampshire, really got some significant snows. And that's largely driven by that sort of warm advection frontogenesis there that we just sort of described for you. And this here, just comparing the, Roddy had mentioned before, this is the high resolution ensemble forecast. This is on the left is the basically the 1 hour mean snowfall. It's a great way to sort of depict where you may have some really heavier snows. Basically, if you think about it, if it's snowing, if you start to see values of like 1 to 2, that means it's snowing at 1 or 2 inches an hour. And you could see this matches really well with the image on the right, which is the radar image occurring at, basically on Thursday. What you'll find is that you'll see those axes of heavier snows towards eastern Massachusetts, and then also towards the interior, up towards northwest Massachusetts, further upward into central and southern New Hampshire, southern Vermont as well. And we sort of mentioned before that really central New York into a good part of southern Vermont and into New Hampshire as well also got some really heavy snows. In this case here, Binghamton, New York, they exceeded 40 inches of snow just with this one event. And that's it's sort of in its context, that's half of its seasonal snow falling in basically in a matter of 24 hours. It's very, very impressive. And this here is a radar image that actually we saw on Twitter. And what you'll find is you'll see these bands of really heavy snow. That's an area that's colored in yellow. That's real intense snow. In some cases, you'll see the tweet there, 15 inches in 3 hours. That's 5 inches an hour. As this band just sits over the Binghamton area. So it's really a very sort of an impressive snow accumulation, for central New York, and certainly that expanded later in the day to include southern Vermont and into central and south central New Hampshire as well. And then besides, we talked about the flash freeze and the heavy snow that tends to take most of the headlines when it comes to winter storms. But we also had some minor coastal flooding that was a concern as well. And we had coastal flood advisories in effect for eastern Massachusetts, especially coinciding with the high tide. And you can see some images on the right there of Vineyard Haven and Nantucket, which show some minor coastal flooding there, just as water just washes over some of the roads there. Fortunately, we didn't see as great an impact. But we'll get into that here in a minute. But we do want to mention that we did have some minor coastal flooding with this event as well. And this here is basically a plot of the water levels at various points. You'll see across eastern Massachusetts, Nantucket's pictured, Chatham, and Boston as well. And what you'll see here is the difference between the two images is what the difference between the two little graphs there is what we call storm surge. And storm surge, by definition, is sort of the abnormal rise of water above the predicted astronomical tide. And the predicted astronomical tide is that color that's shaded in blue that you'll see on several of these little curves here. And so we could find the difference between the two at any point in time. We can sort of figure out what sort of storm surge that we'll see. And that's a factor when it comes to coastal flooding. In this particular event here, Boston had 1.9 feet of storm surge. Again, that's water above the predicted astronomical tide. Shifting gears towards Nantucket, now we're talking at 2.1 feet, and then towards the Chatham area, around 2.5 feet. So in general, we're looking at about a 2 to 2.5 foot storm surge across eastern Massachusetts, specific to this event. Now, the other sort of factor that goes into coastal flooding is wave action. Larger waves tend to crash on shore, so you get that sort of erosion effect just from the waves crashing on shore. But fortunately, the impacts just from the waves themselves were fairly limited by the fact that seas out across the open waters were generally less than 20 feet, and sort of near shore across the bays and sounds, generally around 7 to 10 feet. So sort of in general, a minor sort of coastal flooding sort of situation specific to this event. All right, so we'll just sort of close here with just a summary points here. So 3 factors here that led to heavy snow in the Northeast specific to this event. The first one was the very strong mid-level convergence in Frontogenesis. Again, that was sort of centered around 700 millibars, or about 10,000 feet above your head. Likewise, we had stronger lower-level easterly flow at 850 millibars, or about 5,000 feet above your head. And that sort of helped to draw some locally upslope heavier snows in the mountains. We also had sort of a coastal front sort of set up as well. And that sort of led to just on the west side of that, you can get some heavier snows on the coastal front. But its major factor, too, was also the flash freeze that would result later in the day across southeast Massachusetts, portions of Rhode Island as well. And we see these are sort of typical features that we often find associated with winter storms. And what we'll often see is we'll see sort of 2 bands of heavy snow. Very similar to this event here, where we had one that was inland towards northwest and western Massachusetts, and then the other one closer to the coast. We saw again that sort of local maximum there across eastern Massachusetts, again fairly close to the coast. And when it comes to winter storms, sort of basically historical winter storms, what we tend to find is that when actually we talk about this a lot, sort of where the low tracks is pretty significant. Specifically, when the low tracks near New Jersey and Nantucket, instead of out towards what we call the benchmark, but that's basically a latitude longitude coordinate, 40 degrees north and 7 degrees west. So when you have a low that tracks west of there, you tend to find the higher snows more inland than you do near the coast, and especially near the 95 urban corridor. On the other hand, if it tracks near the benchmark, then you start to see the more heavier snows tend to be more focused towards that, very populated 95 corridor, covering, parts of southern Connecticut, Providence, and into the Boston area. Looking at the different models, the GFS was found to be too far south with the storm initially, and then it tended to trend, back towards the north. And that's sort of a known sort of, systemic bias with the GFS forecast model. It tends to move things along too quickly, and sometimes the errors initially, once we start seeing these storms 3 to 6 days out, sometimes the positional error can be upwards of hundreds of miles. So it can be pretty. It can certainly sort of be sort of pretty far off initially at first, but eventually it'll sort of lock back in. We do also want to point out too is that there's actually a new version of the GFS coming out in February, and that performed much better. But we still have to watch for that sort of systemic bias there to see if that sort of course correct that sort of mid course. The other thing too is we don't just look at just the GFS forecast model as well. We looked at several models, and there are ensembles as well. Those sort of the ensemble models being a difference between when we sort of initialize a model to get sort of different answers, different outcomes. But the one thing we find is that if the European model, or that's the ECMWF, and then there's the UK Met model, that's run out of England. If both of those are in agreement on sort of a big hit, then odds are that it tends to be more probable that we'll see a sort of a big impact winter storm. So yeah, that's all that's our presentation here for tonight. I'll pass it over to Joe.
All right. Thanks, Andrew and Rodney and Hayden, for a good review of that storm. We'll go ahead now and answer as many questions as we can. So just a reminder, I should have said this at the beginning, go ahead and use the chat box, which is on your control panel on the right, and you can enter a question or comment in. So let's see. The first question I have is from John. Did high pressure to the north help fuel the pressure differential, making what appeared to be a weak low stronger? And Hayden, I'll hand that to you because I think you had that part of the presentation.
Sure. Well, a lot of it actually was the thermal gradient, and that is basically there was very, very cold air over northern New England. So remember that where we looked at about 10,000 feet up, we had a big temperature gradient at that level. So that's really what fueled the heavy snow, and that's why it was displaced so far to the northwest of the actual surface low pressure system. So you can have different gradients at different levels of the atmosphere. In this case, I don't think that heavy snow was driven by the actual surface high and the surface low. I mean, they were factors. I think looking up into the mid levels of the atmosphere, say around 10, 15,000 feet, that was, I think, the real reason that we got this heavy snow, especially in parts of central New England.
All right. Thanks, Hayden, and thanks, John. Good question. From Michael, and I guess I can answer this one. It's just a basic question. Could you explain the correlation between millibars and height in thousands of feet? Sure. So in meteorology, when we are forecasting, we look at things on what's called a constant pressure level instead of a constant height level. So instead of saying, well, let's look at 2,000 feet, 5,000 feet, 10,000 feet, we look at things in terms of pressure. And that helps us correlate pretty much, areas of warm air or areas of cold air, because really in reality, the heights say when we talk about, the 850 millibars, we say it's 5,000 feet. It's not always 5,000 feet. Sometimes it's a little below, sometimes it's a little above. So it's a little complicated, but without getting into too much detail, it's a little easier for meteorology to use a constant pressure surface as opposed to a constant height surface. So I hope that kind of makes sense. So we will always see these things in millibars, and we try to always kind of put an equivalent height in feet. It's kind of just an average. It's not really, specific to that height. So from Tom, in terms of frequency, if there were no other major snowstorms this winter, could the December 16th to 17th be called a freak event? Hayden, I'll let you answer that one too. That seems like something of your alley.
Okay. Well, it certainly was a, very significant winter storm. I think no matter what happens, not so much in our area, but a little ways north, say in parts of central and southern New Hampshire and central southern Vermont, into parts of New York, southern New York state area around Binghamton. This is a historic storm by any measure. So it will be remembered, I think, for years to come. I mean, when you get over 40 inches of snow, even though areas like that are used to a lot of snow, that's quite the excessive amount. And the way it was done was somewhat unique in the sense that we didn't have a really strong low pressure system at the surface. Like I said, you don't always need that, but a lot of times you are looking for that. And I think that's why the forecasts, further north did not have nearly that much snow. It would have been hard to forecast that based on what was the model guidance was showing, was indicating the threat for a significant snowfall, but not to those type of levels.
Yeah, and I think also, Hayden, it's been a while since we've had a really decent snowstorm in December. It seems like the past, maybe 5 years, our winters have been all backloaded, like late January into March. So, I know we kind of talked about that a little bit. It's been a while. This was the first one I think I can remember in several years.
Yeah, technically the one in 2019, it was right after, it was the end of Thanksgiving weekend. So it was Thanksgiving ran late in 2019, so the actual snowstorm was on December 1st through the 3rd, but theoretically the rest of December wasn't too active last year, and then January and February, obviously, there wasn't much of anything. But yeah, we've kind of seen, I guess one of the trends I've seen in the past 10 years is our winters, whatever we end up getting seems to really be focused in a 6-week period where we kind of get everything. And then outside that, there's not too much.
Yeah, and I think we're kind of going through that right now. So we're kind of in a quiet period. So I guess we'll see what happens after this 6 weeks is up. You never know. And Tom has a follow-up question. I can take it. What's a shortwave? I guess one of us mentioned that. If you check out Tom also, and for anybody else interested, if you haven't checked out our Winter Weather 202 webinar, it's on our YouTube channel that goes through a lot of the terminology and a lot of the models and things that we used to forecast. So that'll probably help you understand this a little better. But a shortwave is just kind of think of a small ripple in the atmosphere. You see that, maybe the polar jet stream a lot of the times on weather maps on TV. It's just kind of a smaller kink kind of in that large jet stream. And what it does is as the shortwave approaches, it provides lift. So it's kind of a large scale source of lift. Andrew and Hayden talked about things like frontogenesis and warm advection. Well, a shortwave also induces lift in the atmosphere and helps produce precipitation. So good question. And hopefully we're not being too technical on these, but definitely check out Winter Weather 202 on our YouTube channel because it goes through a little more of this in some detail. All right, let's see. From Joe, a few days leading up to the storm, the Canadian models and the globals were showing a mid-level banding over New York and Vermont. He had a hard time buying into the 35 to 44 inch amounts it was showing, but actually verified well. So I don't know, Andrew or Rodney, you want to handle this one?
Yeah, sure. Yeah, thanks for the question. This is Rodney. Hindsight is always 20/20. And I mean, given the overall setup, and the Canadian solution, and this was only one or two runs of the deterministic guidance, and we talked a lot about the ensemble versus deterministic guidance. Different models, so they have different number of members, and so you really need to see the majority of the members hopefully converging on a similar solution to give you confidence as a forecaster. So I would say that there were not really any compelling evidence to really go above 2 feet of snow in any of the locations, and that includes our neighboring offices that have to deal with the 40 inches snowfall. And so, I would say that the HREF did highlight the potential for heavy snowfall. They indicated 2 to 3 inches per hour snowfall rate is possible, but really we were not expecting 5 to 6 inches per hour snowfall rate. And even if you were to forecast this amount of snowfall, the placement of the snow band is really not exact science. So you can kind of do the ballpark, but given the narrowness of the band, even a shift 10 to 20 miles, it's can make a big difference. So in that case, it would really be more of a nowcasting situation. So we can only do our best to give the public the most reasonable amount of snowfall to be expected, and also include the higher end amounts. But situation like this, 40 inches per snowfall, it's almost like a very rare occurrence that hopefully going forward with the forecasting enterprise can pick out this extreme events further in advance. So that's just my 2 cents.
Okay. All right. Thanks, Rodney. Let's see. Comment from Jonathan, and I think he's correct. And good to see you with us, Jonathan. The total at Boston, I think, was 13.1. And I believe that is correct. I think we had 12.9 listed. So we'll give you the extra 0.2, Jonathan. I know, as you said, we need all we can get, so we'll take it. And from Tom, the snow-water ratios for Boston and other locations, I believe, guys, and correct me if I'm wrong, I think we're mostly in the 10 to 15 to 1 inch range, except maybe toward the south coast it was a little lower. But for the most part, I think 10 to 1 to 15 to 1 would have done it for this storm. You can correct me if I'm wrong.
Yeah, this is Andrew. No, that seems like that's what it transpired.
Okay.
With milder temperatures, lower snow to liquid ratios towards the southeast Massachusetts.
Yeah, I know we weren't as concerned with the heavy wet snow, except right along the south coast and just inland from the Cape Cod Canal. So for the most part, it was a fairly light and fluffy snow, which we like. Let's see, from John, how far north did the rain snow line get before the cold front moved through? Andrew, you want to tackle that one too?
Yeah, specific to the rain snow line.
Yeah, I think it got up to Plymouth County.
Yeah, no, it did get up to like northern Plymouth County, like towards like the South Shore. But yeah, no, that's sort of where it sort of that's how far north it sort of made it before that coastal front came down and sort of switched the temperature profile over from rain to snow.
Okay. And another from John. Ooh, I don't know who wants this one. Would it be possible to explain what a gravity wave is? Hayden, you probably can do that. I'm trying to think in simple terms. I could give it a shot if you don't want to, but I'll give you the first crack.
Yeah, I mean, a lot of times it is difficult to kind of explain when you're dealing with rapid pressure changes within the atmosphere, basically what can happen is you can get areas where you have very strong lift, and then not too far away from that, very strong subsidence, and subsidence would actually limit the precipitation. But where you had the very strong lift, you could be getting extreme snowfall rates, 4 or 5 inches per hour, and then a little ways away from that, you can be getting nothing. And because of that pressure difference, you can always get very localized, strong wind gusts kind of out of nowhere. So that would kind of give a basic definition. I don't know if you want to add a little more to that, Joe.
Yeah, that's probably the easiest way to explain it. It's just due to different pressure changes in the atmosphere, not necessarily at the surface. So you kind of see clouds like this on some days, like a wavy appearance to the clouds, which kind of implies some turbulence actually in the atmosphere where the air is rapidly moving up or down. Almost like what you'd see on the beach, when the waves come in, you see that rippled effect in the sand. It's very similar to that, but think of it as air rushing up or down. So you see it occasionally in some of the stronger winter storms, especially, we mentioned this one wasn't so strong as a surface low, but aloft there was a lot going on, and that's the kind of situation where you see it. But it's also conducive to producing very heavy snowfall rates, and sometimes even you can have lightning and thunder out of these things. So, or strong wind gusts, as Hayden mentioned. So that's probably the easiest way to explain it. And I hope, John, we're not being too confusing because it's pretty technical thing. Let's see, from Gary, and I'll hand this one to Andrew since he's worked in areas with mountains. Did the topography of the area affect reported snowfall totals?
In general, it does. I guess in this particular event, I don't think it necessarily had a strong influence to the topography and the higher terrain, but we typically see the higher snowfall sort of across, or at least sort of in a local maximum sense, across the terrain. It's colder there, so that certainly is a factor. But with this particular event, I think most areas got a good, with exception for like Cape Cod, most areas got a good 8 to 16 inches of snow across our sort of area of responsibility, a good part of southern New England. So I guess in that sense, we didn't typically see the really strong, what we call the upslope component. Basically, that's the component of the wind that goes up the slope of the mountain. And what will typically happen in that case is you'll get, sort of your heavier snows to fall on the upwind side of the mountain, and then on the other side, you typically see a snow shadow, or basically see less snow on the downwind side of a mountain range. That's sort of how I'd probably answer that sort of question.
Yeah. All right, thanks. And Andrew, I'm going to throw another one at you here too from Kevin. Does warm air advection play a role in how intense frontogenesis gets?
Yeah, it absolutely does. And Hayden sort of mentioned too the convergence at 700 millibars that we saw with this particular event, and sort of that's sort of another factor that besides just the warming temperatures that we call warm advection. You also that sort of having that sort of pile up in one spot that we saw, that 80 mile per hour southerly winds across basically the southern half of southern New England, sort of basically piling up with an area where the winds are basically sort of light out of the east. So we see that warmer air advection sort of banking up against that area of what we call convergence, and that's where we see the the really intense sort of bands, what we call frontogenesis.
All right, thanks, Andrew. Let's see. I've got a question here from John and a similar one from William, so I'll handle these. John wanted to know, was an area of upper level low pressure associated with this weather system, or there was only a surface low? And William wants to know why was an Obamagenesis for the storm, and they're kind of related. There was initially an upper level low moving east, I believe, from the Tennessee Valley, the Ohio Valley, but it actually was opening up or weakening as it reached kind of New England. So, typically you'd think, okay, it's, that's not going to favor a strengthening storm because the system is opening up aloft, it's called. So it's not going to strengthen the low. And in this case, that's what happened. If you remember on the first map we had of the storm was actually weakening as it went from New Jersey to New England. The pressure was going up from, I think, 995 millibars to 1,000 millibars. So it was actually weakening. So we see bombogenesis, like, remember the January 4th, 2018 blizzard. That's when you have an upper level low closing off or getting stronger or deeper as it crosses our area. So this was almost the opposite, but and normally, I remember a few days before the storm, we were saying, oh, this isn't going to be a big deal. It's a low that's opening up aloft, and the surface low is the strong. But, surprise, you got to look at the ingredients a little bit more, like Hayden was showing, and there was tremendous speed convergence in the mid-levels, and as Andrew showed, frontogenesis, and those two things really combined to produce some pretty good snowfalls out of this storm. So it's not always as it seems at first look in meteorology. That's why we always have to dig into the details a little bit. Good questions, guys. Let's see. I'll give this one to Hayden from Gabriel. Was this storm considered to be near blizzard conditions?
Sure. Yeah. This storm was not considered to be blizzard conditions, and the reason being were the wind speeds. So technically, you generally need wind gusts 35 miles per hour or greater for 3 consecutive hours with visibility below 1/4 of a mile. You didn't meet that criteria. One of the things we were lacking is Joe was talking about just a minute ago, we didn't have that rapidly deepening low pressure system. It was actually weakening. So the surface winds, I mean, it was windy, but it wasn't like we've seen in some of our the blizzards that you remember, like the January 2018 storm, the February 2013 storm. We've had so many the last 2 decades, the January of 2005 blizzard. We just didn't have the wind, so you need the winds and the heavy snow to bring blizzard conditions, the 35 mile per hour and 1/4 mile or less, and you need it 3 consecutive hours.
All right. Thanks, Hayden, for the definition. Just a couple more, and then we'll be wrapping up here. Comment from David, first of all. For Bradley, there was 12.3 inches of snow, 0.58 water, ratio of 21.2. My guess, David, is, first, thanks for doing the math, and you did it correctly. I believe that water equivalent, 0.58, is a bit too low. With a lot of these automated stations, the ASOSs, they don't measure the melted snow too well, so I believe that was a little low. I think it was a little, maybe Hayden, if you remember, probably around closer to 1 inch or so out in the Hartford area. I'd have to check some of the reports out there, but
yeah, I think so, Joe. That's something we struggle with the automated gauge, is what to do, how to kind of refine the data, because when they don't calculate it correctly, especially if it's a colder snow, and it's blowing a little bit, it can be problematic. So we kind of look around the area too and see what some of the co-op observers have reported, because they actually do it manually.
Right. Yeah, that's just a function of the automated gauge. But way to go, David. You did it correctly. Very good. And finally from Tom, and I'll open this up to any of you guys. Do you remember what the lowest central pressure was for the low? I think we had the 995 millibars on there, but I'm not sure if that was actually the lowest or just at a given time.
Yeah, I can answer that, Joe. I mean, it's possible it was a little bit lower, like a couple millibars, but it certainly wasn't much lower than that. And as you said, it was opening up. As the upper level was opening up, the surface was weakening. You'd see it was 1,000 millibars when it went by Nantucket. One thing to add to, so the strength of the low pressure is a factor, but it's also the high pressure to the north. So let's say you had a real strong storm, like a 975 millibar low, with like a 1,000 millibar high to the north, it'd be, significant. But if you had that same 975 storm with a 1030 millibar high, you have a very strong pressure gradient. So you're not only, you're windier, you usually have a larger thermal gradient, which can result in heavier snow. So there's a lot of factors going into it. Again, in this case, the low levels weren't, screaming big snowstorm, but if you looked about 10,000 feet, 15,000 feet, it was. So those are the things that, we have to take into consideration. A lot of things to put together there.